Since ancient times, humans have looked up at the sky, marveling at the mysterious paths of our planets. But it wasn't until German astronomer Johannes Kepler unlocked the secrets of planetary motion that we truly began to understand the mechanics of our solar system. So what are Kepler's laws? We'll start off with Kepler's first law, the law of orbits. Basically, the planets don't move in a circular path around the sun as you might suspect, but rather an elliptical orbit, with the sun being at one focus. Kepler's second law, the law of areas. The line connecting a planet with the sun sweeps out equal areas at equal times. In other words, when the planet is further away in the elliptical orbit, it moves at a slower velocity compared to when it's closer to the sun, so that cover the same amount of area in the same period of time. Kepler's third law, the law of periods. The square of the period of a planet is proportional to the cube of the semi-major axis of their orbits. In simple terms, this means if you increase the distance between the planet and the star, the period of the orbit will increase rapidly. So now we know a little bit more about Kepler's laws. Let's delve into the investigations and see what we can understand using these laws that we've just learned. So for the remainder of this video, we're going to be looking at a few simulations using the PhET program. So what I put up on the screen right now is you can see the Earth and the Moon. This is not to scale, this is just to model. I'm just going to look at what happens when the Moon orbits Earth. And one thing you're going to notice is that there's some slight movement of the Earth. I can probably zoom in to show you that a little bit more in detail, but you can probably see that small movement of Earth. The reason why we're seeing this sort of wobble comes down to the center of mass, and we're going to go into a bit more detail about that after we look through into these examples. So here we can see the sun and the Earth, and we are looking for the center of the mass, the balance point between the two planetary bodies. Within this example, there is very slight movement, and the reason for that being is that the center of mass is very close to or next to within the sun because of how massive the sun is. Now, when we double the planet's mass, the center of mass slightly goes nearer to the planet, but because of how massive the sun is compared to the planet, it's almost negligible. In the case of halving the sun's mass, the center of mass will move further from the sun and a bit closer to the Earth. However, the sun is still quite large, so it's hard to see that wobble. Going back to the Moon-Earth scenario, the Moon-Earth mass ratio is much smaller than what the star and planet was. That's why the center of mass is a little bit further from Earth than what it was from the star, and that's why the wobble is a little bit more noticeable. So now we got the star and the planet back up, but now it's to scale. Now this is the Earth and the sun. So this distance from here to here is all 1 AU. So the distance from the star to one marking here would be half an AU. So what we did is we moved the planet to a few different distances to see what the effect might be. So when we actually made the distance actually 1/4 of what it was originally, so 1/4 AU, we found it to be only an orbital period of 31 days. When we did half AU, we found a 170-day orbital period. When we did 1.5, we found 545 orbital period. And when we did 2 AU, we found 967 orbital period. So when we had a look at these measurements, so the orbital period towards the distance, so while they're not perfectly consistent, they do generally support Kepler's third law, showing that as distance increases, so does the orbital period. Based on what we have observed, a planet closer to the sun requires a greater orbital velocity to counter the sun's strong gravitational pull. In our solar system, this would be Mercury. According to Kepler's third law, a planet closer to the sun has a shorter orbital period, meaning it travels around the sun much more quicker in terms of linear speed to maintain its orbit. What you can see is since Mercury is closer to the sun, it will have a smaller distance, so it will have a smaller R value. A smaller R leads to a higher orbital velocity, as velocity is inversely proportional to the distance. Therefore, Mercury will have the fastest orbital period. What will be the slowest orbital velocity in our solar system? We can use the same logic to know that this would be Neptune. Using the same formula, a larger distance means a greater R. This means that our velocity will decrease due to their inverse relationship. From this experiment, I ended up learning so much. I could practically see and witness how velocity and distance altered the orbital period. I was able to get a much deeper understanding of Kepler's laws, visualizing the differences in the center of mass, and just pulled in all the knowledge that I learned from the course and put it together into this video. So thank you for watching. I hope you guys learned as well.